Hi and welcome to Mathematics for Machine Learning. Today we will discuss a generalization of Taylor's theorem to the multivariate case, and we will basically derive tools that we can use to better understand optima of high-dimensional optimization problems. In order to get to Taylor's theorem, we will first generalize a theorem that you might already know from univariate calculus, namely the mean value theorem. So this univariate mean value theorem says the following. We have a function that is defined on an interval between a and b and outputs a real number. This function needs to be continuous and differentiable on this interval, where of course the outer 2 points a and b are not the same. Then there exists some point from within this interval such that the derivative of f at this point c is equal to f of b minus f of a divided by the difference between b and a. So f of b minus f of a divided by b minus a. So what this means, you can see in the following picture. So we have our interval a, b. We have our function values f in this direction. So here we have f of a, here we have f of b. And this is the function between a and b. And somewhere between these 2 points, there needs to be a third point where the derivative at this point equals to the ratio between the difference in the function values and difference between a and b. So means that if we look at the difference between a and b, so this is b minus a here, and here we have the difference between the function values. So this is f of b minus f of a. The ratio of this difference in the function values and the difference in the inputs of these functions need to be equal to the derivative at this point. Now, as we can see on the right side, there can be multiple such points depending on the function. For example, here we have our point A, here we have our point B, and we see that there is one point here where this is the case, and there's another point here where the same thing holds. Now that we have reviewed the mean value theorem in a single variable, we have to think about how we can generalize it to functions that have several variables, so that have a vector of inputs. So let's say we have a differentiable function f that takes a vector's input and outputs a real number. So it goes from Rn to R. It's differentiable. Now, one way to generalize this function is we can fix 2 points x and y, so these are two vectors, element Rn, and define a new function g, which takes a scalar inputs from the interval 0 and 1, that is equal to f 1 minus t times x plus t times y. Remember that we said t is in the interval between 0 and 1. So if t equals to 0, then this will just be 1 times x plus 0 times y. So it will output f of x. And if t equals 1, then we will have f of 0 times x plus 1 times y. So we will have f of y. And for values between 0 and 1, we will interpolate between x and y as the input of the function. So we basically move. So you have your vector x, element Rn, and you have your vector y. You're basically moving between these two vectors as input. So here we have some 1 minus t x plus t y here in between. G obviously is also a differentiable function, but it's a function that only takes a single variable, which means that we can apply the standard mean value theorem to G. So remember that we said the mean value theorem looks at the difference in the function values at 2 points, x and y. In this case, we look at the difference in the function values between 1, so where we only look at y, and 0, so f, where we only input x. And this should be equal to the derivative of g at some point c within this interval. Remember that we have here divided by 1 minus 0 in the mean value theorem, so we have divided by 1. We can ignore that part below. However, since g of 1 equals f of y and g of 0 equals f of x, we can compute the derivative of g at this point c that lies between 0 and 1. So here we have g of 1 minus g of 0. This equals to the derivative g prime of c. How do we get here? Well, the way you compute the derivative is using the chain rule. So we have a function f. We first compute the gradient of f, so the outer times the inner part of this function. So the gradient of f at 1 minus c times x plus c times y times the derivative of the inner part, which equals to y minus x. So if we take the gradient of this inner part, we get the gradient of 1 minus c times x, the gradient with respect to c, plus the gradient of c with respect to c of c times y. Here we get a minus x, and here we get a y. So the result of this gradient calculation equals to the gradient of f times y minus x. Equivalently, we can define y equals x plus h. So h is a vector that goes from x to y, so it would be this vector here, that's h, then we can say that f of y minus f of x, where we put f of x to the other side, so this is this part here, plus this part here, where y minus x equals h, so y minus x, and then the gradient of f at this weighted average between x and y would be the sum of x plus some value t between 0 and 1 times h. Now this multivariate generalization of the mean value theorem that we just derived also allows us to get an estimate of the difference between f of y and f of x. And we can get this estimate using the Cauchy-Schwarz inequality. So by applying the Cauchy-Schwarz inequality to the right side here, we get that the absolute value of f of y minus f of x needs to be smaller or equal to the gradient at this interpolating point between x and y and the absolute value of the difference between y and x. Now, if this gradient is also bounded, so it means it never takes a value of infinite or minus infinity as any of its entries, then we know that this also needs to be bounded. So it also needs to be always finite. In this case, we call the function Lipschitz continuous. Now we have looked at functions that take a vector as input, but still compute a real valued output, so scalar output. Now, what if we have a function that computes a vector as its output? So we have some function f, and remember, here we have a boldface f, because f is actually a vector. So we take as input a point in this interval between a and b, and we output a vector boldface f, but it's still continuous and differentiable. Now, let's look at this f. So f is a vector that has components, little f1, f2, up to fn. Because each of those fi here, these component functions, are functions themselves. It's now functions that, you could always just compute boldface f, so the output vector, and just ignore all but say one entry, in this case f2. Then we could define this function that computes the vector f and discards all the components except for one as the component function fi, for in this example I equals 2. In this case, we can just apply the standard mean value theorem, because this component function is again a normal univariate function. Now if we pick x from this interval and x plus h also from this interval, then we can just apply the standard mean value theorem to this component function, because we have a normal scalar function. So the mean value theorem says that the ratio between the differences in the function values at the 2 points, so fi at x plus h and fi at the point x, divided by the difference between the 2 points. And what's the difference between x and x plus h? Well, that's h. So divided by h equals to the derivative fi at x plus some point ti times this difference. Of course, instead of dividing by h here on the left side, we can also take the right side and multiply by h. So fi at x plus h minus fi at x equals to the product of the derivative of fi of x plus some point ti h, where ti element 0 and 1 times h. Now notice that our ti has this index I, because we're kind of done here with the things that we can generalize. There will generally not be a single t that fulfills this property for all the component functions. So unfortunately, each component function, well, we have to determine a different ti in principle. Let's briefly go back to normal univariate functions. So we have our f, goes from r to r, it's continuously differentiable. Then we can state our mean value theorem. Remember, the 2 boundary points that we look at are x plus h and x. So h is again this difference between these 2 points. Then the ratio between the difference in the function values and the difference equals to the derivative at some point x plus some t star between 0 and 1 times h. So this outputs a point between x and x plus h. Or we can take h and multiply it again to the right side. So f of x plus h minus f of x equals to the derivative at x plus t star times h, and multiply this derivative with h. So this is one thing that we can derive. There exists some t star between 0 and 1. A similar looking formula we can actually derive by looking at the fundamental theorem of calculus. So what is the fundamental theorem of calculus? It is the theorem that states that if you take the derivative of a function and you integrate the derivative from x to x plus h, you get the difference in the function values back. So you have f, and here you have your point x, and here you have your point x plus h, and the function goes somehow between this. Then the difference in these function values can be obtained by looking at the derivative between these 2 points And the derivative, well, it will be negative around here. Then it will be close to 0 here. And then it will go positive around here. Well, if you take, let me redraw this, it's not ideal. So the fundamental theorem of calculus connects the function to its derivative. It says that if you look at a function, so we have a function f that goes somehow between x and x plus h in an interval. What we're interested in is computing the differences in these function values. So basically we want to compute what is this. We can compute it using the derivative. So if we look at f prime, goes to 0 here, and then it goes positive again. The integral, so the area here under this curve, might even be slightly negative here. So computing the integral over f prime yields exactly this difference here. So the difference between f of x plus h minus f of x equals to the integral from x to x plus h of the derivative. Equivalently, instead of working with some u that lies in this interval, we can also integrate over a variable that goes from 0 to 1 by reparametrizing our function. If we reparameterize our function in the integral, we're basically doing a change of variables, so we have to multiply by the derivative. Thus, we get f prime at x plus t times h, integrating over this t, which interpolates again between x and x plus h, times h. So this looks very similar to the mean value theorem, but instead of saying that there exists some scalar t star between x and x plus h, we integrate from x to x plus h. Thus, the value f prime at x plus t times h at some particular point t star has been replaced by the mean of the function. So we're computing basically an average of the function by integrating over this function. So it's a continuous form of taking an average. Using this integral, we can actually state a similar generalization for functions that are vector values that take an input vector, so a vector element Rn, and output again a vector element Rm, as long as this function is continuously differentiable and we have these points come from Rn, the input. So then, using the formula below, we have that the difference between f at x plus h and f of x equals to the integral. Well, we have to generalize, so the derivative before becomes the Jacobian matrix, where the Jacobian matrix is the gradient of a function that takes vectors both as inputs and as outputs. So it's a matrix that is according to the column layout that we have. It's an n by m matrix that computes the partial derivatives of all the components functions of f with respect to all the input dimensions. M component functions, we have n input functions, which means that the gradient or Jacobian matrix is element Rn times m. So this Jacobian is now placed into this integral. We're taking the integral over the interpolation between x and h, which we can do by introducing again the scalar t that goes from 0 to 1. So if t equals 0, we have f of x. If t equals 1, we have f of x plus h. So we're really using a single scalar, we can integrate f from x to x plus h. Now, how do we integrate over a matrix? Well, the output of this integral will again a matrix of the same dimensions. So it will again be an n by m matrix because we're performing the integral component-wise. You can think of this as just doing n times m independent integrals over the different entries of this n by m matrix. The output of this law is an n by m matrix, so we transpose it. Transpose gives an m by n matrix, and we can multiply it by h, which is an element of Rn. Thus, the whole thing here will be element Rm, as it should be, right? Because the output of f is element Rm, so the difference between f of x plus h and f of x is from Rm. So we have just shown that we can write the difference in vector valued functions as an integral over the Jacobian matrix or gradient of this vector valued function. Now, one particular vector valued function is the gradient. So this means that if we have a function f that takes a vector as input and outputs a single scalar, but that is twice continuously differentiable, that means we can compute the gradient and then take the gradient of the gradient, or the Hessian matrix that we already got to know. Then we can apply what we just saw in order to compute the difference in the gradient at 2 points x and x plus h. Or equivalently, we can say that the gradient of f at x plus h equals to the gradient of f at the point x plus the same integral that we had before over the gradient of this gradient. Remember that if f is twice continuously differentiable, then the gradient itself is a function that goes from Rn to Rn. So in this case, the number of input and the output dimensions are the same because we compute the gradient at a particular point, and we get a vector of rate of changes at this point. So it has the same input and output dimensions, but it still as before, a vector-valued function. And because f is twice continuously differentiable, we can compute the Hessian matrix, which is the Jacobian of this vector-valued function. Thus, we can just apply the theorem that we have just shown. So the gradient at f of x plus h equals to the gradient of f at x plus the integral from 0 to 1 of the Hessian, where we integrate over, again, this t that goes from 0 to 1 that interpolates between our 2 points x and x plus h. And then we multiply this output of this component-wise integral, which again is an n by n matrix. So this here is element r n by n by a vector of length n. So the result of this will be an n length vector. So the gradient of f at x plus h equals to the gradient of f of x and this vector that we get by integrating the Hessian and multiplying this integral by h. Now, before we actually state the Taylor's theorem that we wanted to get to, I would like to also remind you of the second order Taylor approximation. So the second order Taylor approximation gives you a parabolic function. So it's a parabolic approximation. It's performed at some point x0. So and it says that f of x0 plus h is approximated by f of x0 plus the gradient at this point x0 times the difference vector plus 1/2 times the squared form of the Hessian at this point x0. Now this approximation has the same gradient as f and the same Hessian matrix as f, but all higher order derivatives would be 0 for this approximation. Now let's get to Taylor's theorem. It's a theorem that is, as we said, used to show properties of optima of multivariate functions. So we can use it to analyze the results of optimization algorithms. Suppose f is a vector-valued function, takes a d-dimensional input vector, outputs a continuous number. It's continuously differentiable, and we have both x and h from Rd. Then there exists some t elements 0 and 1 such that f of x plus h equals to f of x plus the gradient at f of x plus this point t times h. So this is a point between x and x plus h times the gradient. So this is nothing else than our generalization of the mean value theorem. That's the first part of Taylor's theorem. Now the second part, if f is not just once but twice continuously differentiable, then we can use the fundamental theorem of calculus to compute the gradient at a point x plus h as the gradient of f at the point x plus the integral of this interpolating sum between x and x plus h, where we interpolate by letting this constant t go from 0 to 1 of the Hessian and multiplying the result by h. before we actually had a transpose here. But remember that the Hessian is an n by n symmetric matrix, so actually the transpose yields the same thing as if we just write it as this. So we can or we cannot write the transpose here. Yeah. And secondly, there will exist some t element 0 and 1 such that the function value at x plus h equals to the function value at the point x plus the gradient of f at x times the difference vector h plus 1/2 times h transpose the Hessian of f at x plus t times h times h. And with this, I would like to thank you for today. And next time we will use Taylor's theorem in order to look at optima of multivariate functions. So see you next time. Bye bye.